And he's like, okay, go do it.
Okay.
Oh, what's oh, rip.
I didn't even know it was a thing. He basically told me at the beginning of semester he was going to give me an A, and I'm at like a 78 right now.
Oh, yeah, I'm at a.
I have more gold stars than anyone else, so I'm getting an A in that class.
Or as much as ever.
Okay.
I mean,
All right. Shut up. Okay, so we're gonna. How many of you were here last time? Raise your hands. Here last time, last Friday. Okay, so for those of you who weren't here last Friday, I'm going to start the discussion and work a lot in the context of what we talked about last Friday. You don't necessarily have to know the details of it, because what I'm going to do is, while I work through things, I'm going to try and focus on the steps that pretty much anyone with a little bit of calculus background can understand, okay? But if I say some things, some words, if I write some things on the board that you're not familiar with, that's because you probably weren't here last time, or you were here and you forgot it. So a couple of results from last time that we're going to make use of heavily today is the following: a definition, a p-form, which I'm going to just generically call by the letter F, and then I'm going to put a p in parentheses to remind us of the size of the form. A p-form F is a totally anti-symmetric 0p tensor, where, for those who know a bit about tensors, 0p just means it's got p dual vector indices and no vector indices. And we talked a lot about why it needs to be anti-symmetric, writing down bases, lots of different features, but a couple of other important things that we introduced were the exterior derivative, so derivatives of forms. And you can take different kinds of derivatives of forms, but the exterior derivative is particularly nice because, first and foremost, it's automatically invariant under coordinate transformations without needing to specify a metric or introduce Christoffel connections. So it's actually a very, very nice derivative, particularly in topological context, which is what we're going to talk about today. And the exterior derivative of a form is defined as, and I have no idea why I wrote it like, right, the components. Yeah, I'll just write it in terms of the components. So if F is a p-form, then the exterior derivative has how many indices?
P plus 1.
P plus 1. The exterior derivative takes a p form and turns it into a p plus 1 form. And the expression for that is p plus 1 factorial, and then you make an anti-symmetric combination of all of the indices of the derivative operator and the form itself. Okay, so those are the components in the exterior derivative. But importantly is this observation we just mentioned, that it takes a p form to a p plus 1 form. So again, there's a lot of details, like what the hell does that expression mean, these brackets and these indices and all that stuff. But that's really not going to play a huge role in what we're going to do today, because we're going to work with such low dimensional examples that the derivatives are actually going to be pretty trivial, Zach.
So I just, in our definition of our derivative, or our exterior derivative, we have a partial derivative. So it seems kind of strange to me that we're saying that this exterior derivative is invariant of coordinates when we have an expression in terms of derivatives with respect to coordinates.
Oh, I'm sorry. So I'm sorry. Maybe I shouldn't say coordinate invariant. Okay, so there's coordinate invariance, and then there's coordinate covariance. And so what we want in general is we want to be working with objects which transform like tensors. And that means that the equations we write, if they're written in terms of tensors, the left side and the right side transform homogeneously. And so you can say if an equation is true in one coordinate system, it has the same form in any other. Of course, equations in physics often derive from action principles and Lagrangians, and in that particular context, this would correspond to a symmetry and invariance, but these are normally equations, like equations of motion. So what I should say is that without having to introduce Christoffel symbols, this particular derivative gives us back a tensor. That's what I should say. Okay. And a lot of what I just said would make more sense to people who took general relativity and less sense if you haven't. So, but it's not that crucial for what we're going to do today. Okay, so fun facts which we observed last time about some of these things is that if you take the exterior derivative twice, if you take the second exterior derivative of any p-form, what do you get? Zero. Okay, so that's going to be something we're going to make use of today. Another fun fact is that in d dimensions, the value of p, that is how big the p is in the forms, can only go from 0 up to d. The smallest it can be is 0. It can be negative. That doesn't make any sense. And the largest it can be is the actual dimension of the space, because if you try and get a larger p than that, then you can't anti-symmetrize these indices because you're forced to repeat them. Jacob, if you're going to make a joke, I'm not going to call on you. Question, though, I will be happy to entertain it.
Is a question in the form of a joke, or vice versa?
No, we've got to get through a lot, so I don't want to spend time joking. And then last observation is that p-forms are naturally, it's not to say we can't have fun, we just have to be quick on our feet, are naturally associated with p-dimensional surfaces. Okay, so those are three observations that we saw sort of borne out in detail the last time. Again, if you weren't here, that lecture is posted online and the notes are posted so you can take a look at it. But these are three particular results that we're going to make heavy use of today, so that's why I bring them back up. Okay? So again, even if you aren't comfortable, we're going to kind of see how these things get used in the course of the discussion today. So, all right. Okay, so what I want to talk about now, I'm going to start with something that's going to sound sort of like rigorous, but trust me, I'm not a mathematician. I am going to be anything but rigorous. And if you are a mathematician in the room, I'm going to go ahead and apologize in advance. And you're welcome to exit. But I am going to give you sort of the physicist's operational way of thinking about these things. I'm not going to prove anything. I'm really not going to be rigorous. There's lots of other more elegant ways to say what I'm going to say. But I just want to kind of get to the meat of it and eventually show you how to sort of intuit these results and how to use these results. And I'll come back at the very end. So I'm going to go through a lot of abstract stuff, and then at the very, very end, I'm going to tie it all back with something that's super easy to wrap your head around. Okay, so if you just bear with me, it'll pay off in the last few minutes. So, so to get started, we're going to have to put ourselves in some context. So we're going to consider a manifold. And if you don't know precisely what a manifold is, don't worry. I'll give you one feature of the definition later on, but there's a very rigorous way to define what a manifold is. If you want to really know what that is, you can take my general relativity course. I'm going to call that manifold M, and it is going to have a dimension D. Okay? Most of what I'm going to talk about today is going to be in the context of spatial manifolds, so we're not going to talk about space-times today. But most of what I'm saying can be generalized to manifolds of space-time. And then I'm going to let omega p of M be the set of all p-forms on M. Okay? So any p-form. Now so there you could write down an omega 1, an omega 2, an omega 3, all the way up to D, okay? And each of those, so like omega 1, would be the set of all 1 forms that you could possibly put down on M. And then omega 2 would be the set of all 2 forms. Okay, so this is just a set of all possible forms of different levels of penis.
So
But the biggest P can ever get is the D.
So what?
The big.
So, all right, guys. All right. So Okay, so what do I mean by this? So this set. Okay, so to give you an idea of this set, first of all, we can introduce a basis of one forms. And so we would have a dx mu1, a dx mu2, all the way up to dx mu d. So this is a one form for each dimension of the space. Okay, and then any p form in the space can be written as a set of coefficients or components times a wedge product of a sufficient number of these basis one forms. Okay, you would only use p of these if it's a p form. Okay, we can define d of them, but we would only use p of them to define a p form. Okay, now these indices mu1, mu2, mu-p, these are all summed over. So another way to think of this is a linear combination. So you pick all the different combinations of the p individual one forms you can, and they each get a coefficient. So to make this really concrete, because concrete always helps, let's just use d equals 3 and do p equals 2. Okay, and this is a case we've already looked at. So f2 in this case would be something like this. We would have a component for, and let's just suppose my basis is dx, dy, dz. Okay, so 3 one forms for d equals 3. And so I would have okay. And so essentially, an arbitrary two form in 3 dimensions is just an assignment of these coefficients. Okay? So any two form in 3 dimensions you can write in this form just by tweaking the values of the coefficients. Okay? Well, hopefully it's somewhat evident that this forms a vector space. Because really and truthfully, you can think of these as basis vectors in a vector space, not the space itself, okay, but in a just an abstract vector space where this is one axis, this is another axis, this is another axis, and then these are the components of an arbitrary vector broken down into those on those bases. Okay, so this omega p is generally going to form a p-dimensional vector space. Okay. Okay, so with that in mind, we're going to define, okay, so we have one set of forms. This is the omega p's. Now what I'm going to do is I'm going to introduce another special set. Or actually, this is a general set defined on the manifold M. What I'm going to do now is introduce 2 special sets of forms. Okay? So the first is consider. Where do I do this? I'll do it over here. I'll do it over here because I'm going to erase all that in a minute. Okay, so now consider p forms, which of course are automatically a part of that. Consider p forms such that the following is true. Let me see where I am up here. Yes. And these sets of forms I'm going to call A. So, and one of these forms is, of course, on this set of forms. And dA equals 0. Okay? So this is the subset of all forms whose exterior derivative vanishes. So there's a certain sense in which you can kind of think of these as constant forms. Although it's a little more complicated than that because this is not the normal derivative. Okay. But just to give you something to anchor this to, you can kind of think of this as constant. Okay. So I'm going to call that set of all forms which satisfy this condition, I'm going to call that set just APM. Okay. Now everything that I'm defining is with respect to the particular space you're dealing with. So for example, this set omega p would be different if I have different m's. And we'll see that. And this set AP will be different for different m's, and we'll see that in some examples. Okay? These are called closed forms. So, and I'm going to use that word a lot. When I say the word closed forms, all I mean is that the exterior derivative of the form is 0. Okay? That's set number 1. The second very important set is to consider p-forms on omega p such that, and I'm going to call these b just to distinguish them. Of course, these are on omega p. And this time, bp can be written as the exterior derivative of some p minus 1 form. Okay? So again, here the forms are kind of constant, their derivative is 0. Here the forms can be written as the derivative of another form. Okay? So the set of these, I'm just going to call BP of them, and these are what are known as exact forms. All right? Now, folks, bear with me. All of this seems completely unmotivated. It's very abstract, but I swear to Christ, at the end of it all, it's going to make sense and be intuitive. And that's the beauty of this. If you can hang with me, it's going to make sense at the end. Okay? Okay, so we could ask ourselves, is there any overlap between these two sets?
All exact forms are closed forms.
Exactly. So one observation we can make is that all exact forms are necessarily closed, since d of dc of anything is automatically 0. So if I have an exact form and I take its exterior derivative, db is d squared c, but that's automatically 0. Okay? So what we notice is that everything in this category is in this category, but what's really interesting is the things in this category which are not in this category. Okay? Those are the things that are going to be super duper special. Those are the things we're going to want to find and analyze. Okay? So does everyone understand why everything here automatically exists here? It might not be obvious that there could be things here that aren't here, but we'll see that in the course of examples. Okay? All right. So our goal now is going to be essentially, hopefully you've had a chance to write all this down. Our goal now, write it down. No one is writing anything down. Are you writing down notes? No, you're probably just writing my notes. All right. Okay, it's funny. Why am I thinking anyone's writing anything I say now? Anyway, it's fine. Okay, what was I going to say? Yeah. Okay, so without any further ado, consider. Actually, I'm going to reserve this for examples. So what I want to do is kind of tease out the set here that is not contained here. So the extra ones here. And so to get at those, we consider the quotient. We'll call it HP of m. And that is going to be given by AP of m over BP of m. Okay? Now, before I actually sort of get into the guts of what this quotient means, let me actually point out a useful observation, and that is that this set AP forms a vector space. Okay, and we can see that it forms a vector space because, first of all, we have scalar multiplication, because if I have k times a, okay, and I take the exterior derivative of that, where k is a constant, well, that just comes out of the exterior derivative. And so this is still 0. So I can multiply a closed form by a scalar, and I still get a closed form. And then if I take two of these forms, say A1P plus A2P, okay? Their linear combination is closed because of the linearity of the exterior derivative, because this just distributes. Okay, so the sum of two closed forms is also a closed form, and that's vector addition. Okay? So these form a vector space, and then you can go through a similar argument to demonstrate that these form a vector space as well. So we've got three vector spaces: omega, the set of all p-forms, the set of closed p-forms, and the set of exact forms. And literally a vector space, I mean, you know what a vector space is. Like x, y, z in 3 dimensions is a vector space, and you have 3 basis vectors, and you draw an arbitrary vector, and then you decompose it into its components. Okay, so now the reason I point that out is because when we talk about this quotient, we're actually making a quotient of vector spaces. We're taking a vector space and quotienting by another vector space, and so let's quickly talk about, have any of you encountered vector space quotients? Okay, it's okay. It's not a sophisticated idea. It's just one that no one's probably like really spelled out for you. So let me give you an example of a vector space quotient. So let's take the vector space of R3. This is just 3 spatial dimensions, and I usually am going to use x, y, z. And then I'm just going to quotient that by the 2-dimensional vector space xy. Okay. So vector space quotiented by a vector space. And what the idea of the quotient is as follows. Actually, sorry, let me give you the definition here, and then I'm going to apply it to here. So what this quotient means is that HP contains, sorry, actually we'll say it this way. So after I do the quotient, I get the following result. 2 elements of AP are equivalent if they differ by an exact form. That is an element of P. Okay? So what I'm saying is, if A1 of P is if the difference of A1P minus A2P is some element of the exact forms, then I am effectively going to call those things equal. Okay? They're different here, but the quotienting says I'm going to ignore any difference in the two that comes from an exact form. Okay? Now that's the definition we have there, but we use the exact same definition here. So a way to say this is if I take an arbitrary element of R3, which you know what this looks like from physics 1, we got Vxi hat plus Vyj hat plus Vzk hat. And then I take an element, actually I'll call that V1. And then I'm going to take another vector V2. And the vector V2 is just going to be the vector V1, and then I'm going to add some element from this space that I'm quotienting by. Okay, this is like adding on an exact form. So I would have some Uxi hat plus Uyj hat. And then in the quotient space, I would say, I'm going to say that those two things are effectively the same. Okay? Now let me just give you the bottom line of this, because it's pretty straightforward. All this is saying is, I really just ignore the x and the y components. Because the only thing that I can truly specify is the z component. Okay? Because I'm free to change the x and y's, and if I change the x and y's, I'm not changing the thing in the quotient. It's always equal to itself. Okay? So effectively what happens is this quotient reduces to a one-dimensional vector space, which is just the z components of everything. And so there's kind of a really, really weird abstract division going on. Okay, a three-dimensional space divided by a two-dimensional space, it obviously gives you a one-dimensional space. Okay? Yeah.
And so when we're taking that quotient, the result is the part of the space that is unaltered. Okay.
Yeah. Okay. All right. So now in this case, you might say, well, okay, so if I know the dimension of this space and the dimension of this space, then I just do this simple thing. Well, unfortunately, these spaces are a hell of a lot more abstract than these. Okay? So it's going to take a lot of work to figure out what's going on here. All right? So what we're going to do is we're going to just get this through some examples, in the course of some examples. And truthfully, like, there are some beautiful theorems associated with calculating these things, and I'll show you some of them. But generally speaking, like, you got to treat almost every case a little bit differently, all right? Using all of the definitions that I've given you. Okay, so are there any questions so far? Because we're now just going to start taking all this machinery and diving into examples. Ask a question, Madison.
No.
Okay. All right, so just to make people giggle, and because it's funny, you always encounter cool words in physics, right? Creation operators, killing vectors, annihilation operators. One of my favorite in all of this kind of stuff is that the dimension of HP for a manifold M, so that is, what is the dimension of the quotient vector space, is called the Teeth Betty number
It's awful.
of M. And yes, it's B-E-T-T-I. Okay, so if you've ever heard the term Betty number, which is very...
I bet you haven't.
It's pervasive in topology. That's what the Betty numbers are referring to. Okay, so great. I'm one-fourth of the way through my talk, and I'm halfway through my time. So we're going to do some examples. And in the course of doing examples, we're going to do honest-to-God calculations. So let's start with considering the zeroth quotient for any manifold M. And so I guess I should give this thing a name. HP of M is the, so this is this set. This is the one you get after your quotient, is the Pth cohomology
What?
of M. So when I refer to cohomology, when I say that word, I'm talking about this set H. So this is the zeroth cohomology of M. So let's talk about what the zeroth cohomology would be. So first of all, so if I'm talking about the zeroth cohomology, then I'm talking about P equals 0. I'm talking about zero forms, okay? But zero forms are forms which don't have any of those dx, dy, dz's. They're literally just functions. So a zero form you can think of as a smooth function defined on the manifold M. So C infinity just means that you can take as many derivatives as you want and it will never be discontinuous. So that's the definition of smoothness, or our operational definition of smoothness. So literally any function over the space, as long as it's smooth, you can take as many derivatives as you want, will constitute a zero form on the space. And then we have some trivial results. For example, elements of elements of A0 of M are closed. Okay, remember A is the space of closed forms. So, of course, this means dA of 0 is 0, but the exterior derivative on a zero form is just the functional derivative. So this literally just means df, or this just means df, or written in terms of its components, it's just df dx mu equals 0. Okay? So what this means is that in this incredibly simple case where p is 0, we're literally just saying that a closed form, a closed zero form, corresponds to a constant. Like literally, it's got the same value all over the space. Okay? these f's are locally constant. Now, I threw the word locally in there, and we'll understand why I threw the word locally in just a minute. However, if the space M, and I haven't said much about it, all I've said that it's a manifold and has all the nice properties that manifolds have, but if M is actually disconnected, and what do I mean by that? I literally mean that I have two pieces where the set of these is M, but M is composed of two things which are separated. Like you literally can't continuously get from one to the other. Then locally constant f's need not have the same value. Okay? Because locally constant just means as you move around infinitesimal from point to point, it doesn't change. But you can't do that to get from here to here. So that means that an f defined on this whole space would have a value here and a value here. It's constant here, but there's no reason why these two constants have to be the same. Is everybody on board with that? Okay. All right, so this means that, for example, we could say that the function f for the coordinates on the first piece is 0, and the function for the coordinates on the second piece might be 1. Okay? Two constants, but they're different. And then okay, so what freedom do I have here? For each, and obviously I could generalize this, I could throw in a third piece, and then this would now have, some other thing that I could add, maybe make it 3 or 4, whatever. So what do I have going on here? For each disconnected piece, I'm allowed to specify a constant. And those can be different. That's a vector space, where each disconnected piece is a basis vector, and the constant that I'm picking on each of them is the component along that particular basis. So A0 of M is a vector space with dimension equal to the number of disconnected components. Literally, if I have 3 disconnected components, the dimension of this is 3. If I have 2, it's 2. If I have 1, it's 1. Okay? Now that's only half the story, right? We now got to figure out this and then form the quotient. Okay? But good news. What's that? Say it loud.
0.
0. Why is that 0?
Because you're taking the exterior derivative of p minus 1, which...
Yeah, the exact forms have to be you have to be able to write them as this, where p here is 0. But there's no minus 1 forms. Okay? So it turns out that the space of exact forms is exactly 0. Okay, and this is where your normal math intuition your spidey senses might get tingling, but it's actually okay. H0m is A0m quotiented by B0m, and this is just nothing. You're not dividing by 0 in the same sense as they're doing as a function, but this is basically quotienting by nothing, which is not quotienting at all. Okay, so this is just A0. So what we found is this nice interpretation of the zeroth cohomology on any space. This is always going to be of the form r to the n, where n is the number of disconnected components to the space. So the zeroth Betti number of a manifold is the number of disconnected components. Right? Now, hopefully, that sort of smacks of the idea of topology, right? You know, one component is topologically different than having two disconnected components. So we're starting to see the emergence of topological properties, but it's going to get much richer. Okay, this is sort of the most basic result. To go any further, unfortunately, we're going to have to dig into specific M's. Okay, so the first non-trivial example that I'm going to hand you is, or sorry, this is actually a somewhat trivial example, but so the first concrete example I'm going to give you is H1. Okay, we can do 0 for any space now. But now I want to do H1, and the space I'm going to pick is going to be particularly simple. It's just going to be the real line, the infinite one-dimensional real line. Okay, so that's a particularly simple space. And it's one that you're very comfortable with because that's the space you usually do functional calculus on. When you write f of x, x is usually the real line. Okay, so let me see. Okay, here we are. So for this example, we're working with a one form because we're doing p equals 1 here. A one form is expressed by f of 1 is just some function of x with one of the, or with the one form basis vector along x. Okay? This is a top form. Can anybody remind me what a top form is?
The highest.
Yeah, it's the highest p form you can have in a space. That's when p is equal to d. So this is a one form in one dimension, so it's a top form. And one thing that's true for any top form is that the exterior derivative of it must vanish. Because the exterior derivative would have to give you one higher, but you can't go any higher. Okay? So d of a top form is automatically 0. Okay? So the space of one forms is actually equal to the space of closed one forms, because all one forms in this example are closed. Sorry, we're being specific. If I leave this out, please remember to write it in. Okay, so what about exact forms? So for exact forms, I want to find a one form B that is the exterior derivative of some C0 on R. And the question is can I find one forms of this type? And so if I write B1 as B of x dx, I can write any one form in this format. I can write any one form in this form. Any one form in this format, in this way, in this means, in this manner. But this has got to be expressible as the exterior derivative of some 0 form, but the exterior derivative of a 0 form is just an expression that looks like this. Okay, so really what I want to know is, can I find a bx that is the derivative of some function c of x? And, well, we know that this is possible because we can just take c of x to be the integral of b of x dx. All right. Okay, so if you give me a b of x, I can just find the c of x by integrating it, and then by taking the derivative of both sides, I'm getting exactly the form that I need. Okay. So what we have found is this funny result. The space of all one forms is equal to the space of all closed forms, but any form on this space is also exact. So this is also equal to the space of all exact forms. Okay? And this means that the first cohomology of the real line is 0. because I'm taking a space and quotienting it by itself. Okay? Literally, the thing you're quotienting by is collapsing all of these elements in this to 0, but this is quotient, this is taking everything in this and collapsing it to 0. So this is just 0. Okay? So the first Betti number of the real line is 0. All right? Now, this can be generalized to Rn and leads to what's called the Poincare lemma. And the Poincare lemma just simply states that the p cohomology of Rn is R for p equals 0, because remember, p equals 0 counts the number of disconnected pieces. Well, if you have the real line, you have one disconnected piece. So we expect the dimension of the vector space for p equals 0 to be 1, and then it's actually 0 for all p greater than 0. Okay? So the reason why Poincare's lemma is so important is that what it means is that locally, if I just look at a small region, all exact forms can be written, or all closed forms can be written as exact forms. And the reason I say that is because one of the definitions of a manifold is that locally it looks like Rn. That's one of the main definitions behind manifolds. In a small neighborhood, they look like Rn. But that means that in a small neighborhood, this is true. So the only way that you can get a deviation from this is for something to be happening globally. And that's why these cohomology groups are sensitive to the topology of the space, and they don't care so much about what's happening locally, because locally everything trivializes. Okay. You guys seem so impressed. Rock my socks off. Okay, all right. So now we're going to go through one non-trivial example, and then we're going to just see how all this applies to a more intuitive scenario, or make a more intuitive. Yeah, you just finished the sentence. Okay, so this time we're going to do a circle, S1. And it turns out that most of the interesting results for topology involve compact spaces, or at least some parts of spaces that are compact. The real line is not topologically interesting because it just shoots off to infinity. You can't really screw with it. But if you grab a space and you wrap it in on itself, then you get some really interesting topological possibilities. The most simple thing is obviously just to have a circle, a one-dimensional space that is closed on itself. So that's what I mean by S1. It's the perimeter, it's not the interior, that's the disk, okay? So for a basis of one forms on this space, it makes sense to use d theta instead of dx, because, you know, theta is a good polar coordinate for going around the circle. And then we can write a one form, because we're dealing with the first cohomology, as some function of theta d theta, okay? And then we get to say the same things we said before. This is a top form, so the exterior derivative of anything, of any top form is 0. So we immediately know that the space of closed forms is the same as the space of all forms. All one forms are closed on this space. And then exact is where things get interesting. So before we said, before we said something like this. To find an exact form, we basically had to find a b of theta such that this was true. Okay, that's just exactly what I had before, except everywhere I had x, I put a theta. Okay, so really what I'm looking for is a b of theta, which is the derivative of some c of theta. Okay, if I can find this, then I'm good. Okay, I've got exact forms. But here's the issue. Living on S1 does not come for free. If something, in particular a function, is defined on S1, it has to have a certain property. And what do you think that is? It's periodic, it's continuous. Okay? So all these functions are periodic. And we'll find out that that throws a wrench in the story. Okay? So let's consider what we can do. So first of all, we can take b theta. So we can turn this around and we can say, I can just define c theta as the integral of b theta d theta. Okay, that's the same thing we did last time. And in all of this story, every function c theta, b theta, everything needs to be periodic. Otherwise, it doesn't have any business living on S1. Okay? And by the way, since you live on S2, you're periodic too. You just probably weren't aware of it. So what we can do to sort of make the periodicity manifest is we can take b theta and we can expand it in a Fourier expansion. Now, if you don't know what a Fourier expansion is, don't worry. It's kind of like a Taylor expansion, but it's more useful for periodic functions because it uses sines and cosines. So if I take a function and expand it in a Fourier series, then I have a constant piece, and then I have a sum over a bunch of cosine terms, and then I can also have a sum over a bunch of sine terms. Okay? So any periodic function of theta can be written in this form. But now you see the issue. Is every integral of this periodic? No. The integral of these terms are periodic. You integrate cosine, you get sine. You integrate sine, you get cosine. But if you integrate that, you get theta. Theta is not periodic. Theta linearly grows. Okay? So what we can say is c theta is only periodic if a0 equals 0. Okay? So what we can now say is that the space of closed forms is almost the same as the space of exact forms. The only difference is a single real number, this constant. So from that, you can intuit that the space of closed one forms on a circle, quotiented by the space of exact forms, would be R1. So this is the set of real numbers, and that's what that represents. The freedom to pick this is the set R1. Okay? So a circle has a first Betty number that is 1. Wolfgang's loving it back there. I love my Bettys. I love my Bettys. Okay, so I always get nervous at this point because I'm like, there's no way I'm going to get the rest of this, but we're actually going to do it. It's going to be fun. Okay, so this is where it gets really cool. To do any other examples would just be way too painful. Okay? This took a while. So what I'm going to do is I'm going to give you a very powerful result, and then I'm just going to state the answers for a couple of cases, and then we're going to turn this into a story that is actually somewhat intuitive. So one very, very powerful result for calculating these Betty numbers is what's called the Poincare duality theorem. Clearly Poincare had his dirty hands in a lot of this mess. And what's hilarious is that even though Poincare keeps popping up, this entire subject is called Theorem Cohomology. So Theorem is the one whose name stuck. On a closed manifold M, closed you can just kind of think of as it's not infinite. It's somehow wrapped up so that it doesn't stretch off to infinity. So like a circle or a sphere, that's a closed manifold. On a closed manifold of dimension D, the pth Betty number of this space is equal to the D minus pth Betty number of the space. Okay, so let's just check that in an example. So if M is S1, and I look at the 0th Betti number, so if P is 0, well, how many disconnected components does S1 have? How many disconnected components are there in S1? It's 1. If I gave you 2 circles, it'd be 2. If I gave you 3 circles, it'd be 3. But if I just give you 1 circle, it's just 1. Okay, so this is 1. Okay, by the Poincare duality theorem, if P is 1, then that should also be equal to, or sorry, if P is 0, then that should be equal to 1 minus 0, which is 1. So this should be equal to B1, which we just proved. Okay? So at least it's bearing out in our first non-trivial example. Okay? Now, some more non-trivial cases are the two-sphere. If I take the two-sphere and I calculate the zeroth cohomology, what should I get? I'm hoping you're comfortable at least answering this question in the next 5 minutes. The zeroth cohomology is the number of disconnected pieces. If I have a two-sphere, literally the surface of a basketball, how many surfaces do I have? One. Good, you guys are there. All right. So this is R1. The first cohomology of this, and this is not obvious, is 0. And the second cohomology by the Poincare duality theorem is again R1. If I take a 2 torus, that's a donut, the surface of a donut, what would H0 be? 1. Good. You guys are making me proud. H1 is actually R2. And what would H2 be? R1. Good. All right. By the Poincare duality theorem. So these two mental results are non-trivial. Okay? In fact, you can take this and generalize it to Sn. And for Sn, what you discover is that H0 Sn is R. And Hn of Sn is R, which it must be, and then everything else is 0. Okay, that's highly non-trivial. Okay, here's the good news. We got a couple of examples in hand. We've got a lot of abstract shit that you don't really understand, and now I'm going to make it all make sense. Because of the third property that I wrote when I first came in and started talking about forms, and I reminded you of what we talked about last time. What can you naturally associate forms with?
Surface.
Integrals along surfaces, okay? So remember that if we have a surface of p dimensions inside of a manifold, then there is a natural integration of a p form over that surface. And we talked about this in detail last time, how the p form provides a measure of integration along the surface. So another way to think about the behavior of p-forms on a surface is instead to think about the behavior of surfaces inside of the space. In particular, we want to think about the set of topologically distinct p-dimensional surfaces. Okay? So let's just as an example, let's talk about H0M. Okay? So H0 is a 0-dimensional space. That's just a point. Okay? So if I have some space and I take a point and I take another point, are those topologically distinct? No, because I can just move this point over to this one. Okay? However, if my space is disconnected, are those 2 points topologically distinct? Yes, they are. Because I cannot deform this point into that point. I can't get across the gulf. But that's exactly what H0 is telling us in the context of forms. And of course, if I add in another space, then a point in that space is topologically distinct from these. Okay? But it gets gooder than that. Okay? For S2, well, we've got our results over here. For S2, what we're finding is yes.
Do we need to wind you up again?
Yes. Okay, all right, sorry. Sorry. So for S2, the H0 still gets the interpretation that we have a single disconnected piece. The H1 says, all right, let's take the two-sphere, and on its surface put a one-dimensional closed curve. Okay. The problem with a one-dimensional closed curve on the surface of the sphere is that you can contract it to a point. Okay. So that's actually not a topologically distinct feature of this space. However, if I take the two-sphere and I completely wrap it by a closed surface, all right, then that closed surface can't be deformed to a point. You can't shrink this like you could in this case, and that's why we're getting the cohomology for the second cohomology to be 1. You have one surface you could wrap this with, but in the case of the first cohomology on the sphere, you don't have any one-dimensional surface. So one way to think about it is, and there's a lot of words when you're talking about these curves that I'm leaving out, so we could talk about contractible cycles or simplices, so there's a lot of language that goes along with this I'm trying to avoid because we're out of time. But the idea here is you don't want to be able to contract things to 0. If you can contract them to 0, then then that's effectively saying the cohomology is 0. Okay? So here, any S1 you put on the surface of a sphere contracts to 0. So that's why the cohomology is 0. Here, any two surface you wrap this in can't be contracted, and so that's why we got 1. And then to finish up on the 2 torus, it's a single connected piece. That's why we have the R1. But if I think about one-dimensional curves on the torus, there are exactly 2 topologically distinct curves that cannot be contracted. One that goes around this cycle of the torus, and one that goes around this one. Neither of those can be shrunk to 0, because you can't go through the whole of a donut. And you can't deform them into each other. All right? And that is exactly a reflection of the first Betti number of a 2 torus being 2. Okay? And then similarly, you can wrap the entire donut in a donut-shaped surface that's 2 dimensions, and hence that's going to reflect the top cohomology. Okay? Now, I could just talk for a minute, but in terms of why any of this is useful, obviously mathematicians love this shit. But you might say, and this for me, this is a weird thing, like, you all found these pictures much more intuitive than all that differential form crap, right? So the question might be, why don't you just do all of this with the pictures? And by the way, that's a subject called, unsurprisingly, homology versus cohomology. But you might say, well, why don't you do things with just the pictures? Here's the thing, and I mentioned this last time. There are a lot of spaces that we can just draw, like a torus and a sphere or whatever. But there are a lot of spaces in physics that we actually define by embedding equations into higher dimensional embedding spaces. And so the example I gave last time was the surface of a 2-sphere can be defined using this equation embedded in R3. You're all familiar with that, okay? So a lot of surfaces, and this goes for a much more complex variety of surfaces, a lot of surfaces or spaces are defined by equations. But when spaces are defined by equations, thinking about functions on these spaces is more natural than trying to draw them. Okay, I mean, try to draw this. Good luck. But differential forms are just functions of these coordinates. So differential forms give you a way to tease out all of these topological properties without requiring the ability to actually draw the spaces. You can just work in terms of functions and use calculus. Okay? Now, why are topological properties useful? Well, if I have 2 spaces that are maybe defined by some different sets of equations, and I want to ask myself, is there any way that these 2 spaces are topologically equivalent? Well, one thing that we know is that if I look at the pth cohomology of one space, it better be equal to the pth cohomology of the other space if I'm going to ever say that x and y are topologically equivalent. Okay? So if I define 2 different spaces with some weird equations, and somebody says, hey, are these topologically equivalent? One cursory check is to calculate the cohomology groups for each of them and see if they're the same. If they are, then yeah, possibly they're the same. Okay? But there are exceptions to that. Now this is a math use of this in physics. Of course, you're all aware from a lecture 2 lectures ago that in string theory, we live in 10 dimensions, 6 of which are small, maybe a Calabi-Yau sixfold. So this thing is some convoluted 6-dimensional complex scalar manifold of non-vanishing SU3 holonomy. And furthermore, we have these things called DP branes, which are p plus 1-dimensional surfaces. And an interesting question is, in what different ways can I wrap the DP branes on the cycles of these 6-dimensional manifolds? Well, that's exactly what this cohomology theory is telling us. The reason that's important is because if we want to talk about a D-brane in string theory, this surface, it's got tension. The only way to get a stable D-brane is to have it wrap around something where it can't contract. If I had a D-brane that was literally a disk, it would shrink to 0. Okay? So stable D-branes come from elements of the cohomology class, except for the fact that they don't. And the reason for that is that D-branes have grass. And anything that has grass actually requires elements of the K groups. And that leads us into K theory, which we don't